Hello and welcome to Dr. T Math. In this video we're going to look at some parabolas or quadratics, which are a degree 2 polynomial. In standard form we got ax squared plus bx plus c up here, where c is going to be our y-intercept when x is equal to 0. That's what's left over, so that's when it crosses the y-axis. We got vertex form where h and k are the vertex. That's the minimum or the maximum, the turning point. And then we've got factored form where in this case x would equal negative m and negative n. We flip the signs when we factor using that zero product rule. If one of those is 0, then both of them are 0. We can find the x coordinate of the vertex by looking at negative b divided by 2a. And that's coming from if we had f primed of x, or the first derivative of ax squared plus 2bx plus c, we'd have 2ax plus b. And set that equal to 0, we get 2ax is equal to negative b divided by 2a, and we get negative b over 2a is equal to x. So our middle term coefficient divided by twice the leading coefficient is going to give us our x coordinate there. Let's look at an example where, say, we've got vertex form y is equal to x plus 1 squared plus 1. So if we had our parent function here, we would just have y equals x squared, like so. And then if you know anything about transformations, we're going to move that vertex of this green one up here, 1 to the left and 1 up. So we're going to come up over here. Let's make ourselves a table. We're going to have x, and then y is going to be x plus 1 quantity square plus 1. So we're going to start at negative 3, negative 2, negative 1, 0, 1, 2. Negative 3 plus 1 is negative 2, negative 2 squared. It's going to get us 4. 4 plus 1 is going to be 5. Negative 2 plus 1 is negative 1. Negative 1 squared is 1. 1 plus 1 is 2. Negative 1 plus 1 is 0. 0 plus 0 squared is 0. 0 plus 1 is 1. There's our vertex. And then it's going to be symmetrical on either side of the vertex. This is also called the axis of symmetry. X is equal to negative 1. That's our axis of symmetry here. And so we can see through using the table that plus 1 inside parentheses moves it 1 to the left. That's because at this point now we are where the function, the original parent function, would be 1 to the right. So we're 1 to the left, but that plus 1 means that it's where it would be if it were the parent function. And so we're going to go up like so. And there are no roots on that one. If we took from that y equals x plus 1 squared, that vertex form plus 1, and we turned it into standard form, we would get x squared plus 2x plus 1 plus 1, or x squared plus 2x plus 2. We couldn't factor that. If we try to put it in the quadratic formula, we would get x is equal to negative 2 plus or minus the square root of b squared, which is 2 squared, minus 4ac, which is going to be 4 times 1 times 2, all divided by 2a, which is going to be 2. So we got negative 2 plus or minus 2 squared is 4, 4 minus 8 is negative 4, all divided by 2. And so that puts us over to negative 2 plus or minus 2i divided by 2, which is negative 1 plus or minus I. That I, or those complex roots, means that it doesn't cross the x-intercept, or doesn't cross the x-axis. And so, well, you might be saying, well, what does it all mean? What's this stuff for? What's the point? Oftentimes we'll see in real life there will be either a projectile motion, so something goes up, it comes down, or there might be a profit maximization problem where you were asked to find, given maybe a demand price model, we're asked to find optimal revenue, or the point of diminishing returns, which we can probably just going to use calculus. Say we've got a function, or we've got the profit function given x quantity sold is going to be equal to negative 300x squared. Oh, we'll just say we got some costs in the middle, minus 4,000x, and then plus, well, what could that be? Could be anything. We'll go 1,000. And so we'll take the first derivative, p of x is equal to negative 600x minus 4,000. I suppose we should have done plus 4,000. We'll just do that for simplicity's sake. And then we'll set it equal to 0 because we know that the slope is 0 at the vertex. So we're going to go 0 is equal to negative 600x plus 4,000. Move that 4,000 over, you get negative 4,000 is equal to negative 600x. And so our number of units that we should produce in order to maximize profit is going to be something like, what is it, 600 or 60, 4,000 divided by 600, 4,000 divided by 600 is going to give us 6.66, 6 2/3. And so we're like teeter-tottering between 6 and 7. Maybe if we investigate this a little further, it's just an imaginary example. Not likely that we'll produce 6 2/3 products. We could also use that negative b over 2a, which is going to give us negative 4,000 divided by negative 600. Same thing we just saw a moment ago. That'll give us that vertex. And then if we wanted to find our profit at that point, we would substitute that 6 2/3 into the original equation. So we've got negative 300 times 6 2/3 squared plus 4,000 times 6 2/3 plus 1,000. And that'll be our profit. So we'll square that, multiply it by negative 300, add 4,000 times that, 6 2/3, and then add 1,000 after that, and we get $14,333 and 1/3. So there's a lot we can do with parabolas actually in the real world. A lot of economics classes and business problems have parabolic growth or points of diminishing return or maximums. And then this is the starting off point, the jumping off point for other polynomials, which are all around us all the time. There are all these different polynomial waves that are just kind of like all over the place between sound and different computers and Wi-Fi signals and cellular signals and things. Each of these can be kind of broken down into bits, and you can see there is something similar to or what resembles a parabola in each of these parts. And so that basic shape shows up again and again and again in the real world. And that's been one of the themes here. With mathematics, there's always something in the real world that we can study or model or define using mathematics, even though it seems so detached. It's really just a language or a set of symbols and processes that help us to really understand the real world, rather than it being just a paper-based world that people are kind of making fiction out of. Okay, this has been Dr. T Math. Thank you.